So this talk I have developed is mostly associated with MATLAB, obviously, because it's a signed MATLAB FDP, and I have tried to be very basic, and I will be mostly giving it on as a hands-on session, and I've tried to use whatever I can justice with the Spring Mass on the MATLAB. So I have just taken Spring Mass system as a tool to describe the different facets of MATLAB and how I can use them to solve these equations. Okay. So my contents are very brief. I will try to first give to you the problem and specify what I'm trying to do. Then I will try to discuss the methodology or the numerical methodology which is used to develop this whole scenario, and I will try to use plotting. I will try to use the in the process. I will try to discuss the array pre-allocation, plotting, structure creation, functions. So these things I will try to discuss within the talk. So I've divided this into these five parts. So as you know that it's a very simple problem. Like you have a plate on which there is a mass of there is a block of mass m, and it has been attached to a spring with a stiffness k, and it is allowed to move in the x. So if you apply F is equal to ma, and you have this governing equation which is given on the screen, so the block will move like this in an oscillation manner, and you can solve by and the initial condition which we have right now is that initially, that is at x is equal to 0, so at time t is equal to 0, it is at one distance, and its velocity is also 0 initially. So these are the initial conditions, and we will try to obtain the methodology for them, try to obtain the displacement xt, x is a function of t. So that is what we intend to do. In this intention, we will try to solve the differential equation numerically. So I will be giving you or discuss with you the Euler's method, how I have done the Euler's method. So it's very simple numerical integration. I will also in this evolution of the solution of the this spring mass system, I will cover try to calculate the mass position with time using and we will club the whole Euler's method into a function. Then we will also use structures or box parameters, one box, to do this. And also in the time, we will also discuss how to use debugger and then code analyzer to check the code and the profiler to time the code. So these things in the process I will discuss. How are we going to use this? So again, the methodology is pretty simple, and it is like Euler's integration. And if you know Euler's integration, so you can see that on the right side there's a curve. Its starting point, as you know, its starting point is given. So that means your initial condition for the curve is given, that is a naught. And then you have a differential equation from which the slope of the curve at a naught can be computed, and it is a tangent line. So as you show, the red line shows the tangent line and blue is the curve. Now if you take a small step on the tangent line to a point a1, and along this small step, the slope does not change too much. So a1 will be very close to the a naught. And if we pretend that still we are still on a1, the same reasoning can be applied to the other points, A1 and A2 and A3, and go on. So we will then evolve a polygonal curve, which is joined by A0, A1, A2, and A3, A4, which is very near to the curve. And if it does not diverge too much from the original unknown curve, the error between the two curves will be very, very small. And therefore, the computation time will be finite. And you can write down this as a dy by dt, which will be function of f, which is some kind of function f, and it's and the displacement, that is yt. Now this will be equal to initially at u0. Now n being the number of steps we are going to go from tn to tn plus 1, n being the counter for that, and tn can be written as the initial time t0 plus n times of h, where h is the numerical, is the time step involved. So we can write that yn plus 1 will be equal to h times the function. So that is how you integrate. So it's a very, very simple process, and you must have learned in your maths course this Euler method, and it is, as you know, it's an explicit method. So then you can. So now, since our governing equation is second order governing equation, so we can cast this second order governing equation in terms of two first order governing equation. And so the mathematics is right now given over here, and where Z1, Z2, Z3, and Zn are basically the auxiliary equations, which we call. And and the main governing equation is like Ynt is basically some function of can be function of y, can be function of prime, can be a function of nth order derivative, n minus 1 order derivative. So you write n governing equations for this, and so since our problem which we have in the spring mass system, we have a two-dimensional problem. So second order governing, so we will write two governing equations, which will be your missed one. Yeah. So in the top, if you see that the governing equations are written, and mx double dot is equals to kx plus c. So now I will start the coding of this part. Now you can see that m and k are basically the inputs for this. So, okay, if you will see, so there's another problem. Yeah. So if you will see that, so we will create a new file. So you can see I will start with the new script. Okay. So is this MATLAB command window visible to you? To all?
Yes, sir, it's visible.
Okay, very good.
Can you switch it on in the full screen mode? Maximize it?
Then I have to show something also in the PPT. So
okay,
it
okay.
should be difficult for me to. So I will try to do that as maximum as possible. Okay.
Yeah, no,
so,
no problem. No problem.
Okay. Thank you. I will try to increase the width of this. Okay, I have get rid of the history part over here, and so yeah, I have just added a new script over here. I think a lot of people have talked about this. So we will start with just write the spring mass OD solver. Okay. So now since the inputs are K and M, so we will try to give the mass some input value. Let us assume these to be K, M is equal to 1 and K is equal to 1 as input. Now, since we know we have to calculate. I wish to calculate this for a one oscillation time. So one time period. So if I calculate the time period, it would be simply 2 times of pi and divided by square root of k/m. Okay, so this is, let's put a comment like final time. Now, so we have to divide this into time periods. So let us assume right now as a 10, and therefore the step will be, as you know, that it would be this. So this is so I don't know what it is. So this is the time step. Danish, you are saying something?
No, no, sir. No, sir.
Okay, so I don't know what is happening with this. Whenever this panel opens whenever I push space bar. So as you can see that this now we can check whether this I've taken pi. So but if we can, I don't know whether this pi is there or not. So you can see that it gives you a fourth order. But if you want to change, you can change to the long float value, but it is fine right now. So you have a pi value, and the answer has come out. So that means we have assigned. Okay, there is a slight mistake I have done. So I will change this to H. So H is the command for this, and we will try to. So before saving this, we need to um, save this into a certain folder. So let us save as. So either I can use this folder, or I have another folder in this which has the same code which we discussed, but I will just put it as a demo SPM. Okay, so it's a very, we have started doing this, and so the next I will try to, so how to put the initial conditions, so and how to use the debugger in this one. So before this, I will try to put the initial conditions. So initial conditions would be very simple, as I have already given. That is v is equal to 0 and x initially it is at 1. So now we can use this. And to check the debugger, so what we can do is to initialize the debugger, we can just have to go over here and write some commands like this, like so that the history is cleared and command also doesn't have any history. So if that works or not, then we can, for this we can create the breakpoints. So now you can see that
We are sorry for the interruption. We have lost our speaker, so we are trying to reconnect our speaker.
now everything is visible. So I think I've shared the screen. Anybody can tell, is this visible? हेलो अच्छा लेकिन आवाज किसी की नहीं आ रही सब भागे गया अच्छा हाँ, नहीं नहीं मोहम्मद उमर उमर रहमान कह रहे हैं यस
Some issue, I think, because of some connectivity
so
issue from our side also. So there is some uh, disruption. Although your slides are visible, you can continue now.
okay
Yeah.
so am I visible now
Yes, sir. Now you are visible.
Yes, sir. Now you
are also audible
are
to me
visible. Your
so we can now calculate
okay. Thank you, sir.
acceleration so which is minus kx by km and so therefore we can now run the code. So you can see that it has gone back to the value of x is still 1 because velocity is 0. But initially velocity was 0. But at the next time, the velocity has changed its value from 0 to, see, you can see that initially I have put v equal to 0. You know, where is the initial condition? Yeah, here is the initial condition. So here the v is 0. So it has changed its value from 0 to some certain value. And but since it is only done for one step, so the velocity has been advanced, but x is not advanced. So this is the calculation for one time step. Now if I want to use do it for this for multiple times, so that means I have to use some kind of a loop. Now let us see what MATLAB offers. So you can say that there is a way to check what are the ways where we can do a looping. So the first and the easiest one is the for loop. Okay, so it's for loop is the easiest, and you can see that if I show to you the documentation. So for loop has a syntax that for index which is equal to values, and then you put statements, and then you put in an end to that. So it's a very simple command. So let us implement this. Okay, so that means we have to use the for, and then you have to use a counter. I think I have a counter, and then the range of how you want to index your counter 1 to n. Okay, and then obviously since it is 1 to n, and you have calculated this from the force we have calculated, and then we have to put an end to this. So you can see that the MATLAB editor has itself put, so the better practice, so it have indicated you that this is a loop. Now, now this is very, I don't know what happens with this. Okay. So now you put a tab so that you understand that this is being put into the loop. Okay. Now it is in the loop, but there is no counter to that. So let us do it for 10 iterations. So it has been looped. So let me run again. So you can see that on the workspace part, the X has changed to a value of 4.1266. Okay. Now this value, as you know that the analytical solution for the spring mass system is very exactly is equal to A cos omega t. So if we are doing for one time period, that is the time TF is the final time. Okay, so that means you have to go back to the TF. So cos TF will again be equal to 1. So this value X should have been equal to 1. So, and why it is so? It has not been 1 because we have taken n as 10. And since Euler is Euler time stepping is a first order accurate in time, so it will always require a lot of steps. So in my PPT, if you will look in the PPT, there is a left hand side. On the left hand side, I have tried to do it, integrate it for multiple time steps. So 10, 50, 20, 100, and 250, 500, and 1000. And I have shared a graph with you where X final position with number of time steps. So you can see that after 100, it began to give you some kind of what you can say, some kind of conformity. So let us put 100 over here and run it. So now you can see that it has the X value, the final position of the X has now changed to 1.2177. Now 1.2177, that means if you have, still there is a 20% of increase, in 20% of error. So let us increase this to 500. If you run this for 500, it comes out to be 4% of error. So now it becomes acceptable. Less than 5% for me is acceptable. If you will increase this value to 1000, it will come down to less than 2%. So it's fine. So as you can see that the error increases, or error becomes lesser and lesser if you have more and more time steps. So that means you can, so that is the whole reason why the Euler time stepping is not an ideal time stepping. It's only a first order accurate in time. So, so we should use more or better ways like Ramkutta and all those things. So let us put back the 10 value so that it is demonstration purpose. It is easy to use the 10 value. Okay. So the next slide, which I want to show, is the array handling. So now the reason why array handling is required in this is this. Now we have the initial position, that is 1, and the final position. We do not have the intermediate positions of the mass. So if I want to know the intermediate position, so I have to introduce the arrays, or we have to say this, and we do it through the intermediate, through the arrays. Okay, so then let us create the arrays for position and time. So what I need to do is to modify a few things, like initial, since it's the initial condition. So initially that means X is equal to 1 is 1, and for T we have to create it. So let us do that. So we will So this needs to be modified and put here I, okay, and I have to put the sys since it is a new position. Xi plus 1 is the new position, and Xi is the old position, and this is fine. But if you want to get a graph of x versus time, okay, so you need to have the intermediate positions of time also. So what we can do is that we will create a vector where t1, we will create a vector for t1 is equal to t1 is equal to 0. So this initializes my first position of the vector, and to create the next positions, we will just do ti plus 1 is equals to ti ti plus the time step, okay, which is h. H is a time step. So this I think this will work. So let us run this. So now you can see that there are two vectors which are created here. In the workspace, you can see that there are two vectors which are created, like 1 by 11 and 1 by with the name of the task is T, and it is double, and the default is double. So 1 into 11, and it's a column vector with 11 data inputs. So it's because we have gone to 10, n is 10, so it is 11. And so x is similarly for x. If you will see that, you can see that if you double click over here, then you can see that there are values over here. So you can see that. So it starts from 0 to, and the 11th value is 6.28. So that means you have your variable goes from t0 to 11, 6.28. So that was the t final value. So it is right. Now let us see that what is the value of the positions. So you can see that initially it is at 1. Now since v was initially at 0, so the second position also 1. And then you go on to get 4.126. So that is how you can see that it is arranged in a column vector. Okay. So now, if I wish to see that how this kind of a memory is. So right now what I've done is that it is not, we have not pre-allocated this vector. So we will see that over here, if I see that there's a error from the analyzer. So the MATLAB analyzer gives you that the variable t appears to change size on every loop iteration, okay, within a script, okay. So consider pre-allocating for speed. Yeah. Similarly, the same is given for the variable x also. So obviously, so why we should go for the pre-allocation? So I've tried to include it over here. So arrays have to basically see what have arrays do. They occupy a contiguous chunk of memory. Now, by pre-allocating this array, we reserve that continuous chunk of memory. So each basically, without pre-allocation, what happens that as the each iteration goes, it increases one by one. So if the first iteration n is equal to 10, so it doesn't like in Fortran or C, when you allocate an array, it is given a size n. Okay, so that size, the memory is the compiler or the compiler the compiler allocates the whole chunk of the memory in one size. But since MATLAB, we have not allocated this array and we have created it like a dynamic process. So it is not allocating this memory. So to make the command work faster, we have to allocate this array. So right now it doesn't feel you that it is necessary. But if I will try to show you that how this helps you in speeding your command, speeding your program. So this is how we do pre-allocation. So what we do is that we have to give certain values to this. Okay, so let us. So for this, we will be using a zeros command. So zeros. So now since it is, it was a 1,11 matrix. So let us check this. So you can see that it is zeros are there. So you have 11. Now we can generalize this as zeros. So zeros for 1 comma n plus 1. So n value being 10, right now it should give me 11, same thing back. Okay, so now let us pre-allocate this array. And so let us put this pre-allocation. So right now after this, okay, so let us pre-allocate. Start a new part of the code, pre-allocating the arrays. So once I do this, then what I need to do is this x is equal to zeros. So I will just use the command which I have written over here so that it doesn't give me an error back. Okay, and similar thing has to be done for t. Okay, so once I do this, I will be able to allocate this. Okay, okay. So let us run this so that we check whether it is doing something. Okay. Now I will just put a debugger on this so that I can show you how it is being done. So right now it is like this. Okay. So okay, I need to put a one more debugger. I think. So it's fine. Okay. Let's do this. Yes. So if I do this, so you can see that it has been, there's no value of x which has been allocated because before this there is no x. So now I will just step into this. Okay, you can see that. Yeah. So there is a t array and x array are created. And what is the value of in this t arrays? All are zeros. That is what we intended to do. And that means so every value has been created. The xt array has been created, and all the initial value has been given to it to be 0. Similarly for x also. Let me get rid of this x space. Now, if I continue, the same command which will be reached, the same things will be reached. So once I this, now you can see that. So now you can see that the same values have been repeated. So 11 was 6.283, 6.283. If I check over here again, it is x was 4.12. Now, if I want to calculate what is the speed of by doing this pre-allocation, whether I'm able to get some initial boost to the speed or not. So for this, I just need to So for this, I just need to do runtime check. Okay, so let us do a runtime check with this. So you can see that if I do a runtime, calculate runtime. So this bugger over here opens a profiler. So which is open my next window. So is this the profiler visible to you now?
Yes, sir. It is visible.
It is visible. So if I run this code, so you can see that in the profiler part, so it's a demo SPM. This is the code name, the script name, which we are discussing over here. And the total time of allocation is 0.024 seconds. And the self time. So I always use the self time. So that means this process is indicated. It may be more also. So this profiler gives you 0.024 seconds. Okay. So now if I change, so this was the speed up with the pre-allocation. Now if I don't do pre-allocation, so what I need to do is this, I just need to comment this. Okay, once I comment this is not going to be executed. Let me save this, and then I will just use again the run with time. Sorry. So you can see that initially it was for 10 seconds, 10 iterations, it was 0.24, and now it has come down to 0.014. So it's a quite a gain of 0.01 seconds. Now, the idea will not be clear if I increase this to more. So let us do it for 100, and then we will create a runtime. Okay, so you can see 0.046 without the pre-allocation. Yeah, if I do a pre-allocation like this, okay, so that you can see that again there is a speed up. Okay, now let me increase this to or further. Let us increase this to 1,000. So with pre-allocation it is 0.0345. Without pre-allocation, if I do without pre-allocation, it's 0.046. Now let me increase this further. So let us increase this to 10,000. So without pre-allocation, it is 0.053. Okay, now if I allocate this, I pre-allocate this. Now this is 0.56. So I did a whole bugger thing. Let me increase it further. And then we do not do pre-allocation. Save it and then I run it. Okay. Sorry, I should not run with the time. So it's 0.1 second for 100,000. Now if I change do pre-allocation, save it, then I can find. So with pre-allocation, so it has gone to, okay, I don't know what is happening. It has not changed too much, but yesterday night when I was doing it, So I did find it like this. Okay. So you can see that you get a 2 times of speed up with when you do a pre-allocation. Okay. So let me again do that. I don't know what will happen. So yeah, 0.079. And then and earlier it was 0.1 something. So you can see that there is a definite speed up if you do pre-allocation. And the more the number of arrays are larger, you will always see a lot of increase in runtime. So this is how you use the time this profiler with it. Okay. So now let me start to plot these functions. So how to plot this? So this basically makes the end of the Euler's code, but let us see how we can use to plot these. So let us start a new section plotting x versus t. Okay, now this is very easy. Now let us see what MATLAB offers for plot. So this is the first comes with a 2D line plot. So it's the first documentation help, which is the 2D plot. So it's a very easy 2D plot xy, and there is some plot x. So x is the column vector, y the column vector. You have to give the 2 inputs, and then you can specify the line type. So this is the easiest one to plot. So let us discuss this. And before this, so let us plot this. So it is like plot. So we want to plot t versus x, and then we want to give some line specs. So let us put dash and black. So black, the code is k. Okay. And then you can do that. Okay. So let us run. So the output has come over here. So then we can put it over on the dock. I want to dock this, which is over here. So you can see that this is a plot, which is a very nice plot because we have increased to 100,000. Let us do it for 10 and then see what gives you the answer. So you can see that it's a bad plot. So it's as you increase the 10, so it will be in a good shape as you do. Okay. Now if I want to add this to this of slightly a crisp figure where you can use which figure you can use to show to people. So it will must have x and y and all those things. So I have written a small script which I would like to show to you, and part of the script. So let me copy it from the code. Plotting part. Okay. Yeah. So you can see that I have put this figure 1. So this is the script from here to here. This is the script which I'm talking about, and I can anything which you plot you can call directly. So I could have just copied this. I've just copied this over here. So you can see that now the difference in this is that this plot has been allocated in handle h, and then this handle h we will try to modify with the line width. Here I have modified for uh, line width 2, and then we can modify the global GCA handle, that is the outside of this. So it's a box with box is on, line width is 2, lines are dash, port name, Helvetica, and all those things you can see. So
Sorry
these
to
are the
interrupt,
apps.
sir. Sir,
Hello?
Sir, sorry
Yeah,
to interrupt. There is one question from the participants. You
yeah,
want to ask
bilkul.
that why are you not using v velocity as an array?
No, v velocity is not an array right now.
Okay. And
If you
second
can
question is
see that,
that he is requesting that if it is possible to copy this code in the chat box so that they can try at their own.
yeah, I will do that. No issues. If you want right now, I can right now also copy. If they can do it like that I will copy it. No issues. And uh, v velocity is right now not an array. That is what I'm trying to show, because it is up to you. You can use v velocity as an array also, but velocity intermediate position was not important, so I was not used as an array, because you have to think about what you need to plot. So I want x as a output. So x as a time output I needed. So why to if you want velocity also as an output, you can always put an array middle positions of velocity. So final velocity you always have, but if you want to use the intermediate velocity, if you want to have it, you can put it, make it also an array. So obviously, the more the array which you are trying to use, they will always have a burden on this on the computational side. So you should always think that, okay, which is the thing which we need and which we do not need in time. So unnecessary things. So like right now, since the code which I want try to demonstrate here was only with the help of was only on the x versus t, है ना? So I only needed x intermediate position and t intermediate position. I never needed a what you can call v intermediate position. So therefore, I did not use did not convert the v velocity into an array. So I do not hold the v velocity, intermediate v velocities. Okay. So that is how it is. I will share. So you can, if you want, I can right now copy whatever the code is. I can copy this into the chat box, but I need not to know where the hell the chat box is. Okay. Yeah. So I can see it now. So now, right now, it is all I have pasted. Okay, so you can use that to do it in your end. I will share the script, and once I will finish, I will share the PPT also, and I will share the. So can I? I need to take a call. So if you don't mind. So sorry for the inconvenience. Uh, so so I have shared the code. You can do it on your own, and let me explain to you what the things are there. Okay, so now this is a small script which I have written for enhancing the figure. Okay, so let us run this. I will try to again use the I will again use the debugger for this, and then you will see how it is used. Okay, so what is the effect of every command? Okay, so you can see that I have we have reached on the position of figure 1, and let me step in. So once I step in, so figure 1 is there, and it has been, you can see that it has been made active. So it's now active, and uh, once again I will okay, I back to here again, step in. So oh, 1 minute, गड़बड़ हो गई, गड़बड़ हो गई। Step out करना पड़ेगा, step करना पड़ेगा, step. So once I step, so you can see that so the figure which has been like over there is not there. So that means the figure has been cleared. So CLF basically clears the figure, and then we will try to plot now. So let's plot. Okay, बार बार मैं ये दबा देता हूँ. So step out. So now you can see that the figure has been plotted. So it's the same plot which we got earlier. Now we will try to modify this. So let's do this. So now you can see that I have set the line width to be 2. So it has made the figure is now a dark one. Okay. Now we will try to modify the axis properties. So you can see that the axis has been dark, and the fonts has been set, and everything has been set. Now let me put the label on this. So once I put the label, so then you can see that the T label has appeared on the x-axis, and again I put a label on the y-axis, which is x, and you will see that this will be very interesting. So now the axis square, this title is there, and once I put again, so I have run everything. Okay, sorry. I have to again start to run this. Okay, so step, step. Okay, now I will step, and this is still put title over here. And once I put a title, so you can see that spring mass system title is there, and then I will put this axis command has been done. So axis square. So this command is a unique way of setting that the size of the x-axis and the size of the y-axis will be same. So you can see that from 0 to 6, so since the like x and y dependency is set to 1, so it will be a square figure. Okay, so that is how it has been done. So now if I try to modify the what you can call as the axis size, it's so let me put another command, that is to put the so you can see that the axis command, I have given axis from minus 1.5 to a y-axis. So the axis command, you can see that. Let me show you the axis command. Help on the axis. So it basically gives you limit. So axis has the limits. Okay, so it is just a vector with x-axis, x limits and y limits. So 4 limits you have to give. Okay, so right now I have given it to 0 to 2.1 times of pi, so that it's 6.28 something more than pi, slightly more than pi, and then minus 1.5 to 1.5. So y-axis is minus 1.5 to 1.5, and the x-axis is from 0 to 6.28, so slightly more than that. So it doesn't looks, this plot doesn't looks good. So let me run it for 100 or 1000 maybe. So it looks good. Now this one looks very good. Huh? So let me, don't take it. So now if I want to calculate what is what you can calculate so this is the spring mass system response. Now I do not know whether I have done it correctly or I may have done it wrongly. So let us compare this with the analytical solution. So I will start another part in the code, and which calls as an analytical solution. So analytical solution. Okay. So I will try to, so analytical solution. Oh, there is nothing has been written over here. Solution. Okay. So analytical solution is there. Now I need to create a array which goes from 0 to final time. Okay. So I will use this command linspace. Okay, linspace. So the command is like 0 is the initial point, and then you go to TF, and to check only I will use 3 points. Okay, so you can see that 0 it is the first point, 6.2832 is the last point, and on the midpoint it has 3.1415. Now, so I can use this command to create a T array. Okay. T underscore an array, okay, which will be equal to linspace, not 3, but 51 points. Okay, so I will use this to create an T array. Now, X array, XAN, which is, I am using the suffix for AN for analytical. Now, this is X is equal to the solution to this is cos T. Now, since it is a solution is cos T, so it's very easy. So it is like cos of T underscore An, and U has the solution to this. Okay. So you have the analytical solution built into that. Now, if I use the same command to plot this too, now let us put the same command over here. Okay. So if I use the same command, H is equal to plot T. So now I have to obviously modify AN, and I have to modify AXN, and I want to use dash lines. So you can see the double, and then I want to use R, the red color. So I want to change the color so I can use this. So let us plot. Now, so if I do this, you will see something. So you can see that the original whole thing is gone. Now, so that means I want to hold that original also. So if I want to do that, I need to add another command to this, which is called as the hold on. So I will just need to put, after calculating everything, I will just need to put this command hold on. I can also use multiple variables also, but I would like to do this. And also I will specify another handle, which is H2 for this. Okay, and then I will use the same command, okay, to modify the line size into here. Okay, so this is how we modify the line size, and now you can see what this bugger gives. Okay, now you can see that there is a black line, and on that there is a red line. Now still doesn't give me comfort to see this. So I will use some small square and a point. I will try to show you the symbols also. Now this looks good. Let's give me comfort to the eye. Okay. So now, but which is the analytical solution and uh, which is the line, which is the either solution, we do not know. Okay. So for that, then we have to basically use legend. So you can see that legend. So add legend to x-axis. So you can say label one. So you just need to have label, and then you can put a location also. Okay. So I have done this, and I have just copy this part over here. So you can see that now nicely Euler's method and analytical method have appeared. Okay. So this pushes me to the near end of this. So I have plotted this on the slide. So you can see that. Can create this. Yeah. So now I want to tell you that I am a very good advocate of that the code should be clean. So it should be developed in always a modular way. Okay. So let us develop a function which has Euler as the function name, and then we can call that function, and we can use that function. Okay. So if you do want to do that, what you need to do is this. You want to uh, create a certain kind of a function. So that way, what you need to do is that you create a function which is like this. Okay, so we calculate a develop a function. So let us put this comment, develop a function of the name A, M, N, and H. So these are my input. I will need to use these inputs. I need to calculate these inputs. Okay. Now, if I want to create this inputs, I need, and where are the, so what I need to do is this, those things which are needed over here. Okay, like pre-allocation and so these commands, I will just copy from here and I will put it over here. Okay, now since this was for command, so it will need one more end. So this shows that function starts from here and ends over here. Okay, so this is how the function is there, and I will see. Okay, fine. It's not used, right? Because we haven't given the call. Okay, so now if I want to, so before this, so now, yeah. So plotting this, once I do the plotting, okay, I have to call this function. So I have this call where after H, so block T comma X. So these are the outputs, and I will call the function Euler So I will just copy whatever here it is. Okay. So this is the call which I have done. Okay. So now you do not see any analyzer outputs. You can see. So the call is working perfectly. We get the same code. So if you, I don't know whether we have got. So let us put certain, go back to our 10 and a 10. So you can see that. Yeah. So you can see that there's a lot of errors in this. So that means our code function is working. Okay. So now one important takeaway from here is that the functions are local. So you can see that over here when you will see the workspace. Okay. So I will just put a debugger over here and I will try to run it. So once I run it, I have not allocated T and X over here. Okay. So now I will step in and you can see that the control is directly being transferred from here to here. You can see that now, after this step, now the T and X are, are allocated and pre-allocated. And then now we will step in the initial condition and then we will try to integrate. Step out. Okay, now the control is back to the main command and you can see that TF is calculated and X is also calculated. See that X and T both are calculated. Okay, and then you continue once and say the continue and then the figure appears on this side. So let me dock it for you. Okay, so that is how this is used. So now if there's another thing. So you can see that the code is nice. Code is very nice. It doesn't have so you can have the multiple functions doing things, and you can call this function from outside also. These are methods which are used. So things are just nice over here. I can also use a plotting function to create a plotting function, and then you can use those plotting and line space and all those things. Okay. Now I will also use to show you the need of a structure. Why you want to create a structure. Now we will create a structure that will be containing the values of M and K and how to use that structure. And you can see that the function call will not change. Okay. So let me tell you how to create a structure. I have written this part. So it's a very easy part. So you just need to, after this, you just need to create this, right? Like this box. So this is a box in the structure. And then in that, when the dot creates is like that box, the mass element of the box. Okay. And then there is spring constant element of the box. So we create a structured box and this we equate the box dot ms mass to m and box dot spring constant to the k. Okay, so these values are there. So now you need not to pass k and m, but you pass box. Okay, and here also, since you have passed box, then you have to receive the box also. Now, since you do not know what is box, so then you need to reverse the part. You need to read what is inside the box. Okay, so if you do that, you need to write again these two buggers. Okay, so you can see that the M and K. So inside this, the command will not change. the code will not change. And you can see that. Okay, so there is some valid expression. There is the invalid expression. Might be some missing parentheses. No idea what is doing that. Oh, there was a comma which was missing. Still some error. Unbalanced parentheses. Oh, there also was missing. Now it is fine. Okay, so you can see that I made a small array, a small mistake of not putting a comma separator between box and K and M. So this works fine now, and you can change to see if it really works. Then you can just change. Fine enough. So, so that basically bring us to, you can see that. So how do you create a structure? You create a structure is created like this. You have a box, and then you can put this constant like this. Okay. So this has brought me to the end of my talk, and I would also like to, before I end, I would like to introduce my laboratory and what I'm doing right now. So these are my current research interests. I work in the field of biomedical engineering with few people. We have a turbulence control group in which I work with in collaboration with IIT Delhi people. Then we have some compressible flow dynamics, flow aerodynamics, where I work with a professor in the same in our department, Professor Hassan. And then I also work with in the fluid structure interaction, where I have so we have certain interest in that. So particularly to vortex induced vibration and all. And if you want to work, I will take the opportunity and invite you to work in our lab. And feel free and call me at or mail me at this email because I have written over here. That's all. Thank you, Danish. If you have any questions, please ask.
There is one question from the participant is that what GCA command does?
GCA is basically is the just this the access part. So if you will see the slide of mine, so where is this? Yeah. So GCA basically is the sites part. Yeah. So if you will see that, this is this. So if you want to this access properties, so you have the access properties. So this is the graphics this part is called. So this is the side part of this. So if you want to have the properties, text, and all those things, they are in the GCA panel. So this is the side panel is called GCA. Hello? Yeah. Hello?
Okay, thank you, sir. Thank you, Dr. Fahad
Okay.
Anwar, sir.
Yes. Yes. Very thank you to Professor Syed Fahad Anwar to provide such a deep insight of this MATLAB, which is to be used in engineering, especially in mechanical engineering. So I hope all the participants will enjoy and get some knowledge from this discussion. So if anyone have any question regarding this discussion, so you please, you may ask to the speaker. Anyone have any questions?
So I think this raised topics, Sadhu Khan, to all panelists. What does GCA command does? So GCA is basically, I was just trying to tell you that it's basically the handle to the access. It's a get command access. Yeah, so it's basically the handle to that access. So that GCA stands for the handle to the access. So it basically modifies the access properties to access the
Yes.
access property.
Yes, Dr. Fahad, it is very thank you to you to provide the answers of this. And the Professor Fahad is also very accessible to all the participants if they want to ask any question even after this. So very thank you to the Dr. Fahad as well all the participants in this program. I hope you will enjoy this session and you will go for the next session, inshallah. Okay, very thank you to all.
Thank you,
Just
Professor.
to
Yes, yes, sir,
add to
yes.
this, Danish, I will mail this PPT to presentation to you, and along with the MATLAB script, okay. And
Okay.
if you want, you can share this to the participants.
Okay, sir. Okay. Thank you, sir.
Okay, very thank you. Very thank you, Pasab.
Thank you. Just a minute. I would like to share one more thing. Okay, just
Yes.
when I was making this presentation, I came across to a very uh, beautiful website, which is there. And if you can, if any one of you can go to this website, it will be very great. So it's Berkeley, Berkeley, and then the rotation. So type these two keywords. Okay, so the first hit is basically this website I want to introduce you to. Okay, and I will in this website there are a lot of simulations which have been done. Okay, so Euler representation using MATLAB, Euler's angle pendulum, a book tossed in the air. Okay, I will just I have downloaded this script, which I would like to show to you. Okay, so let me open. I'm sorry I'm boring you for 2 more minutes. Please bear with me, and you will
No,
like
it
the
is
output.
very informative to all the participants.
Yeah, I will just run it to you. So it's a simulation of and dynamics of a book when it is tossed in the air. Okay, so I will just show you the video because this came into my panel. I will just let me just 2 minutes. I will just put these graphics onto my screen. I don't know whether it will come again or there or not. Just a minute. It's always coming on to my parent screen, which is not shared. I just want to share this. I hope it is will come onto that screen itself. No, it is coming always onto my screen. So just a minute. I will just share my parent screen. Then it will be easier for you to see that. Share the first screen. Okay. So so now you see this, Baba. So there's a book which has been tossed and how the rotation and those are going on. So it's a very informative. They have given the scripts, so you can always download the script and then play with it. That. So it's a Berkeley website, and this has been taken from there. So I will, if you want, I can mail you this script also. So I will mail both the scripts and you can play with that. And you can download it from here, from the other part of the screen, the Berkeley website. Okay. Now I am finished.
Thank you, sir. Thank you. Thanks a lot for this wonderful lecture and wonderful illustrations. Thank you, Dr. Basifullah Khan Sahab, for chairing this session. Uh, to this, we have come to the end of our session 2 for this day.